so last class, right, we looked at interstellar media, and then we looked at how we moved from an interstellar media of mostly just gas and dust to stars, right? So quick review, the big, just giant, formless, shapeless, but substantive mass that's between all the stars is generally referred to as a nebula, right? So we have a nebula. Nebula is composed of gas and dust. Gas is primarily hydrogen, right? And dust, and other debris from prior stars, okay? And nebula is huge. It's very dispersed, right? It's very cold. Something has to happen to take us from just gas floating around in a nebula to something that's going to even begin to start thinking about forming stars. And that something is typically like a supernova or a collision of several different nebula together, or even other star formation can get this kick-started by putting out lots of gamma rays or X-rays and UV light, etc. So we can move from a nebula to the next phase by an input of energy that can come from a supernova, from a collision, from star formation. When it does, it can cause the dust and the gas and everything in the nebula to begin to condense and to move. And the first step after a nebula, or the first thing within a nebula, the biggest thing within a nebula, is called a clump. A clump of what? Clump of what? What's in the clump?
Yes.
Gas? Dust? Okay, good. Clump is definitely denser than a nebula, so it is a clump of nebula material. It's also a clump that's going to give rise to what comes next, right? Because within a clump, I will find the next thing, which is? Yeah, say it.
Cluster?
No, we missed a step.
Cluster or
Nope.
Cores.
Cores. So this energy is going to cause these to kind of begin to contract, and gravity is going to start to win over against pressure. And that's only going to continue as we get this. Now, by the time we get down here, things are moving. They're spinning, right? What's that called? Angular momentum. So this thing is beginning to condense, it's beginning to contract, gravity's starting to win, matter's getting tighter and tighter and tighter. What happens is things get tighter and pressed in, that's coming. But first, the thing I'm talking about right now is take your hands, we've done this before, but let's do it again. Take your hands and start to squeeze them together, and they will get
hotter.
Hot. So this thing is we're starting to heat up. Our next step, somebody called it out, is a protostar. As you pointed out, we begin this angular momentum of us collecting together. We're now actually also going to begin to flatten out. And we see this everywhere in the universe. It's not just stars, it's galaxies. Probably the universe itself. Okay. Okay. At this point, we're beginning to flatten out. As we flatten out, a couple of things happen. Right. First of all, the thing that causes us to flatten out is the angular momentum. Right. So you've got basically these poles here. Okay. You began mass in a core. As it begins to flatten out, the stuff at this axis that's furthest away from the core can be lost, it can be kicked out. The stuff that's nearest the core here, in this area, right, is going to be affected most by gravity. The stuff up here is going to be affected the least by gravity. This stuff is going to condense, right? As it does, and as it begins to heat up and it starts to have like solar winds and things like that, that's actually going to push out the stuff in between. Which is how, when we get to down here to the next level, we've got basically, if you were to look at it on edge, you kind of get a space in between, like an empty disk. And then out here, we still have some nebula type material. We'll have a space of emptiness. Well, everything in here has either been sucked in to the star or it's been blown out away because of the star. But the star has had an impact on everything. And now out here, we'll also have the idea of things clumping together, sticking together, right? And this is going to form things like planets, comets, meteors, and asteroids. Okay, and these things are hitting each other, and some are going to stick, and things will get bigger, and some are going to collide, and they'll get sent out of space, and all the while solar winds are blowing, and eventually all the stuff in between will either condense or it'll get blown away. And so you end up at a mature stage with a star, with certain planets. And by the way, why aren't these planets on the same, why aren't they on the exact same plane? I mean, they more or less are, but they're not exactly the same. If you were to look at here's what I'm saying. If you were to look at the orbit, right? One may orbit like this, back and forth, another may orbit like this, back and forth, another may orbit like this. Like, none of them are too far off, only a few degrees, but if there's a central axis here, then there's a central axis here. And it all begins, as we are at this stage, all began along this same plane. But the planets don't necessarily stay, their mature orbits don't necessarily reflect that early orbit. What would cause them to be slightly off orbit? Or their orbits to be slightly off from each other?
Their own gravity.
Their own gravity, so they're impacting each other perhaps. What else?
Their own mass.
Their own mass. Same, those two are connected, right? What else?
Collisions.
Collisions is a big one. As they collide with each other or other things to knock them slightly off the board. Okay. Those are the 2-3 big factors right there. That's good. Okay, so we go from a nebula to a clump. The clump has several cores in it, right? The core may never, it'll go to protostar likely, but it may never become a main sequence star. The number one thing that determines if my core will ever get to a main sequence star is mass. It's got to have enough. It has to have a critical mass so that it gets hot enough so that it can give fusion, right? Okay. What's after protostar? Take those notes.
The disk, right?
What do we call that disk?
Circumstellar.
Circumstellar disk, right? So at this point, we're looking at things having been blown off, our stars beginning its fusion, and now I've got a ring around it, right? At this point, looking a lot like this, like a weird eyeball, right? We're flattening out. What's causing us to flatten out? Momentum, right? At the core, you've got dense, semi-amorphous stuff happening. It's getting that angular momentum, but it's also a lot of stuff in between. My clumps are much bigger, right? Tons and tons of cores in a clump. Of course, the nebula is nebulous, very thin. You know, I could have millions or billions of clumps in a nebula. I could have thousands of cores in a clump, but I'm only going to have one protostar come from each core. Right? And it may, depending on the size, it may or may not ever reach this level. As this is happening, and we're starting to flatten out, right? And the star itself, or the protostar, is beginning to condense. And it's, think about what we're talking about spinning, right? If I had a, I don't have anything else to do it. When you were a kid, did you ever like have something on the end of a string and you spun it around and you put your finger up and the thing began to just tighten around your finger? Or tether, you guys ever play tetherball?
Yeah.
Okay, so you hit as hard as you can on a tetherball when that thing's at full length. It takes a little while for it to get around, right? Right? I mean, you hit it as hard as you can, but still it's going to take a little while for it to come back around. But now, when you're about at the end of the game and you whack it, that thing goes done, right? I didn't have any more energy, I didn't have any more momentum in the last hit than I did in the first hit. But that thing was traveling so much faster because it's radius. It just takes longer to travel around a wide radius than it does a narrow radius, right? So as this star begins to contract due to gravity, it doesn't have more energy, but it's spinning so much faster. And that speed threatens to destroy it, right? It threatens to tear it apart. And so what happens? Do you remember from the video, from the review? Can it hold on to all that mass? Does it want to hold on to all that mass? No, it doesn't. It loses mass, right? Where?
Jets.
Out of these jets, these T-Tauri stars. And so it'll have like jets of material coming out of either end, just shooting material out into space. And that'll happen until ultimately this thing comes into equilibrium, right? It can handle, it's got the right match of speed, of velocity to mass. And fusion begins, and that star, our star is spinning like crazy. All right. Feel good about that? Okay. All of that is really answering the question of how do we get from just dust in space to a main sequence star? Okay. Now we're going to start looking at the back end. What happens at the end of a main sequence? Okay. What is the life of a star? So that was all review, and then today we'll go into some new stuff.
The red giant stage. We mentioned before that all stars become main sequence stars after their protostars.
All right, if you got notes, if you're taking notes, now's your time, okay? We're gonna go over everything he just taught and give you the things that you need to know. It'll be now your second look. You know you'll get one more, at least, before you have to have a final, but why not learn it now? What causes the hydrogen gas of a star from just drifting off into space? Gravity. Gravity. Gravity pushes in. What prevents a star from simply collapsing? Fusion. Provides pressure, which causes this thing to push back out. These are the two factors that influence the size and the temperature of a star, okay? For a main sequence star, these two are in equilibrium. It's called hydrostatic equilibrium or dynamics. Let's go hydrostatic. You might be thinking to yourself, well, all the energy for this outward pressure is coming because we're converting mass and energy equals mc squared. We learned about that. And so surely we're losing lots of mass. Not really. Not compared to the whole. Compared to all the mass there is in a star, almost all of it's there at the end of its life. Very little bit has been converted into gamma rays. Some of it's also been lost to stellar winds. But the bulk of that star is still there. Now it's changed. Some of it's changed from hydrogen to helium, but where has that occurred? In the core. It's another thing we want to think about. When the star begins its life, it's almost all hydrogen. When it's ready to leave the main sequence, this is still almost all hydrogen. The only helium part is right here in the core. All right? So we've lost a certain percentage, it's small, and we're still made up of almost all the same stuff. The only thing that's appreciably changed is the core is now helium. When the core becomes helium, when we've exhausted it all after the star's been around for 90% of its total life and all that kind of stuff, fusion stops because we're out. It takes much higher temperatures to fuse helium into carbon than it does hydrogen into helium, right? We're on the order of thousands of degrees Kelvin to fuse hydrogen into helium. We were on the order of, what number did they throw out there? Like 100 million to fuse helium into carbon. We got to get crazy hot. So, when we run out of hydrogen, fusion stops. When fusion stops, what else shuts off?
Core pressure.
Core pressure. Right? So when, here, let me redraw this. Okay, let me just bear with me. When we look like this is true. When we look like this is true. Okay. When we're out of hydrogen in the core, we're out of pressure pushing out, and now gravity is the only thing we have. And everything comes flying in fast, right? It's going to begin to contract rapidly, right? What stopped it from contracting into nothing in the first place?
Fusion.
Fusion. We needed fusion to provide an outward pressure. And as they point out in this video, as this happens, the star is going to get smaller, right? So the whole thing is shrinking in on itself, including the core. As it does, as gravity does its thing, what did it do before? It created a lot of heat. This is going to create a lot of heat. To fuse hydrogen into helium, we need temperature on the order of 100 million degrees. Think about that. I'm sorry, I said it wrong. Helium into carbon, we need 100 million degrees. Let me write that down. So hydrogen into helium is what, like 12,000 or something like that? But to fuse helium into carbon, we need something like this. That's going to take a while, right? As this stuff is contracting. And long before the core gets to this temperature, all this hydrogen around here is going to reach that temperature. Does that make sense? All right, so as this thing is contracting, and our core is heating up, it's getting hotter, but we're not hot enough for fusion yet. We're going to start to form fusion of hydrogen into helium in an outer shell. Okay? You guys with me? You got to understand this. The core heats up, core is heating, core is contracting and heating, and it's going to keep doing that. But as it does, the layers around it are going to quickly exceed the 12,000 degrees that we need to do hydrogen into helium. And so we're going to get a shell, a new shell of hydrogen to helium outside of the core. This is important. Remember, the definition of main sequences are doing hydrogen to helium in the core. We're now doing hydrogen to helium, but we're outside the core, and this matters. Okay, so a shell of hydrogen to helium outside the core. So our distance from the core is much further out. And now we're doing hydrogen to helium, and what's that going to create? It's going to create more outward pressure from fusion. And there's less stuff out there that we have to push, because some of the stuff that was out there getting pushed is now the stuff that's doing the fusion, and so we are able to push out even further. This thing is going to get massive very, very quickly. Very, very quickly, we're going to get to something pretty big, even as the core is continuing to contract, right? But I've got fusion out here. And so it creates more outward pressure. The effect of gravity is now less, so we're able to push it out even further. While this is happening, this continues to contract until eventually it ignites. Okay, and as this ignites, eventually we're going to get a core with helium to carbon fusion. Okay, we're going to have a shell here of hydrogen to helium, right? And we're going to have these outer layers of just pure hydrogen still. And now we're really burning. We're putting out a ton of outward pressure, right? I got pressure coming from my core, I got pressure coming from my subshell, and so I am really pushing outwards tremendously. Eventually we push so far out that even the weaker gravity impacting these outer layers is able to come back in, and we get back to our hydrostatic equilibrium. definition, we expand until the force of coming from this fusion is again equal to the force of gravity. And at that point, we become pretty stable again. This phase, this point in time, is called the red giant. Okay? By definition, just how by definition a main sequence star was fusing hydrogen and helium in its core, by definition, a red giant is fusing helium into carbon in the core. There is a step, there's a subgiant step, where we're fusing hydrogen into helium in a subshell, but we're not yet fusing helium into carbon in the core. And we really grow rapidly, right? But at this point, we're in equilibrium again. And it can stay here for quite a while, until
Runs out again.
it runs out again. And then everything's going to rapidly come back in, and we're going to, depending on the star, we're going to do this again. If it's a massive star, like a really massive star, it's going to, in what would feel like a blink of an eye, it's going to go. Now this is happening over maybe hundreds of thousands of years. But relative to its entire life cycle, it's just contracting, expanding, contracting, expanding. Each time that it's doing this, we're getting another layer of hydrogen into helium, and another layer of hydrogen to helium, and another layer of hydrogen to helium. And the core is, you know, at first it was hydrogen to helium, then it was helium into carbon, then it's carbon into you know, and we build and we build and build until fusion doesn't produce enough energy for us to go any further. Or until we don't have enough mass to get hot enough. So a star like ours, when it is done fusing hydrogen to helium, it's going to do this. But it doesn't have enough mass to contract down tight enough to fuse carbon into anything else. And so we'll just be left with a core of carbon. All this other gas is still here. But as the star cools down, these outer things will just waft off into space. By the way, do you know what that's called? This core of just pure carbon of a star about our size? White dwarf. Super, super dense carbon on Earth. What do we call that?
Diamond.
A diamond. That's fun to think about. All right. So, I want to think about principles and factors as well as details. What is determining the size of my star? What are the two factors?
Mass.
Okay. Let me do this. What's determining the radius, the diameter of my star?
Fusion.
How so?
Pushing it out.
Yeah, so give me the, what is, it's a pushing, what is that? That's a pressure, right?
You want gravity pushing it.
And gravity pushing it. So these are my two factors, right? Do I have any pressure pushing out from fusion? If so, how much, where? And then gravity. Those are the two factors. When they're equal, what's happening to my star?
Go.
Maintains the size.
It just maintains the size. It's in equilibrium, right? When we run out of fuel, which factor goes away?
The outward.
Outward pressure. So gravity will push it together. As gravity pushes in, what happens to us? We get shrink and we get
Hotter.
hotter. Eventually we get hot enough to start fusing new stuff, right? When we do, I get more pressure. And so our star will push back out. I want to review that one more time, okay? The things that determine the radius of a star, the two factors, are pressure from fusion and gravity. When the two are equal, the star is in equilibrium. It's not getting bigger or smaller. The one that's going to change first is going to be the pressure, right? As we run out of fuel, the pressure will stop and gravity is going to quickly win and condense us. And as it does, we heat up. Once we heat up, we push back, and we push back with a bang, right? It's bigger than it ever was. It's not even close, right? It can do this a series of times as it's going through the giant phase, okay? The amount of energy it takes, the temperature that it requires to fuse helium into something heavier is exponentially larger than it is for hydrogen to helium. So before the core gets to this temperature, subshells will get to this temperature. And we will begin fusing of hydrogen into helium in outer shells, not on the main sequence, which will provide a new pressure and expand us out, right? But the core still contracts and heats up, and eventually it will begin fusion of helium into carbon, and now we'll settle back into another equilibrium. And what phase are we in? Red giant. It can stay there for quite a while, right? And again, we'll begin to run out of fuel, and it may go in and out over time. I want you to think back to your HR diagram. What's all this axis? Luminosity. How intrinsically bright are we? What's this one?
Temperature.
Temperature or mass? Okay, good. Okay, and it is running counterintuitive, right? As I move to the right, I'm getting cooler. Where do I find my, and here's my main sequence, where do I find my giants? My red giants?
Top right.
Above, right? If this was Earth, right, Earth, if this is our sun, somewhere right in the middle, where will our red giant be? Up to the right. It's both cooler and brighter. Both of that has to do with the radius. Right? Just think back to that. We're cooler because those outer layers are further away from the core. So that simply, the outer layers are what's cooler. The inner is much hotter, but we're so far away from it that our outer layers are significantly cooler, right? And yet, we're brighter than ever because there's just so much more out there in the radius. So the position of this has everything to do with the radius. Outer layers are just so much further away from the core, right? All right. You got any questions for me? Let me give you one more thing. He was showing how a star might, as it left the main sequence, it's going to kind of do this, and it might kind of move and jiggle a little bit. Because as it does, and those outer layers begin to expand, right? The star may increase in luminosity and temperature. Then as it contracts again, it may jump back. They get a little hotter as it contracts, right? And it begins to do the next thing, and then it may expand, and we may begin to move that way. So remember, a star never changes position on the main sequence, but it does change position on the HR diagram. And as much as we are used to labeling, okay, here's the main sequence, here are our giants, here's our white dwarfs, it's not like, oh, we just teleport to one to the other. It moves gradually, if you were able to map it over time, as it increases. As those shells, outer shells push out further, they're going to gradually get cooler and gradually get brighter in proportion to each other. And it can contract, and it will get hotter, and it will get dimmer, and then it'll expand, and it'll get cooler, and it'll get brighter, and that will continue on and on. And then we'll talk about what happens from here in the next class or two, okay? All right, so what do we have going right now? I took a picture. That's calculated, not a film. Okay. Let me see that picture. we're on the 3rd right now? Okay, so you're due for review on the 8th. Okay, so we'll review for the test on the 8th, take the test on the 10th. Okay? Y'all have a good day.